A very good morning to all. Myself, Divya PM, coordinator for this webinar. Hope everybody doing well and taking care of yourself in this pandemic situation. Today is the fourth day of our webinar series, and all of you know the topic for the day is On the Real Line, and the resource person is the renowned academician, Professor V. Krishnakumar. We are so excited and feel honored that Professor V. Krishnakumar joined us as resource person. And I think he's the right person to talk about a real life. On behalf of Department of Mathematics, Sri Narayana College, Kannur, I would like to welcome Professor V. Krishnakumar. Welcome, sir. And thank you for finding time for us. In this occasion, I would like to thank Dr. Bijumon R., Associate Professor and Head, PG Department of Mathematics, Mahatma Gandhi College, Iriti, who played a vital role in inviting Professor V. Krishnakumar to this webinar. He is also a part of this webinar and he is providing all technical assistance to Professor V. Krishnakumar, sir. On behalf of Department of Mathematics, I welcome Dr. Bijumon R. to this webinar. Welcome, sir.
Thank you.
Now, I would like to welcome all the teachers and students who are participating from diverse places across the state. Welcome all. I'm sure that this webinar will be meaningful and thought-provoking. I sincerely wish this webinar will become a great success in complementing your knowledge. Once again, I extend a very warm welcome to all who joined in this program. Now, I invite Dr. Bijumon R., who is also a student of Professor V. Krishnakumar, to introduce our chief guest. Bijumon, sir,
Okay.
over to you.
Good morning to all. First of all, congratulations to SN College team for conducting such a wonderful webinar. Let me thank the authorities of SN College, Kannur, for giving me an opportunity to introduce my Professor Dr. V. Krishnakumar sir to this seminar. He is a familiar person to most of us, but it is my duty to introduce him to the younger generations. Professor V. Krishnakumar is an eminent mathematician with more than 45 years of teaching experience. He worked at various prestigious institutions for the last 45 years. He completed his PhD from IIT Kharagpur and he has more than 20 international research papers. Also, his research thesis was supervised by eminent mathematician Professor Jyoti Das from IIT Kharagpur. He supervised 2 PhDs and also did his postdoctoral work from United Kingdom and from Germany. As a student, he completed his BSc from St. Joseph's College, Devagiri, from where he bagged first rank from Kerala University. At that time, there was only one university in Kerala, and he got first rank in BSc at that time. Later, he joined at IIT Madras for PG studies, and he completed the same with the flying colors. From the beginning of the Department of Mathematics, University of Calicut, he became a lecturer there, and later he became professor and head of the Department of Mathematics of University of Calicut. After 30 years of service there, he became the principal of Amrita University, Amritapuri, Kollam. Later, he became the visiting professor at NISER, Bhubaneswar, where he worked for a long time. Later, he associated with the Kerala School of Mathematics, Kozhikode. He received the Best National Teaching Award for Higher Mathematics Teachers, INSA National Award in 2015. He is an eminent mathematician and moreover a teacher who produced lots of mathematicians who are working in various prestigious institutions all over India. The prestigious institutions like IIT, ISER, IIC and so on. Today is an auspicious day because SN College Kannur is organizing a seminar or a webinar by him. Not only that, today he launched a YouTube channel that is devoted for the service of students and teachers who are in the higher education field. Just now it was launched, and I think all the participants in this program will visit his channel and see his videos so that we can learn mathematics from a real mathematician. Also, after this talk, we are going to view his lecture through his YouTube channel as a live stream program, because he is having a separate studio at his home, and we will have his lecture through YouTube live stream, so that all of us have to switch from this Google Meet to YouTube channel, and the instructions will be given by Divya Miss. And after the completion of his lecture through YouTube channel, all of us must come back to this live stream for discussion with him. He is a very friendly person, and we can ask him any question, we can clarify him, and we can also continue our discussion with him, because he has started a YouTube channel and also a separate email ID for discussion with the students. Moreover, within shortly, the PG Department of Mathematics, Mahatma Gandhi College, Iriti, where I am working, going to organize a separate classroom with Professor V. Krishnamurthy as a resource person. So let me conclude. I also once again thank the SN College authorities for giving me these opportunities, and I am very much blessed to have introduced my professor, and also thank you all. Thank you very much.
Dear participants, our lecture will happen as YouTube live streaming in Professor V. Krishnakumar's channel, and discussion will continue with Google Meet. Now, all of you are requested to join in YouTube live streaming. The link is shared in both Google Meet and in our WhatsApp group. Don't forget to rejoin Google Meet for further discussion after the lecture. Thank you all.
Good morning, everybody. I am Krishna Kumar. Thank you for the nice introduction by Divya and Vichumon. Well, it's a great opportunity for me to talk to you. This is the first time I am on a webinar, and it's a very interesting experience, I should say. And after conclusion, I will say what it is all about. But I hope the setup that you have here, that is the classroom, is visible to you. This is named Krishna's classroom for the purpose of recording lectures, and the channel named Krishna's classroom just streams these lectures, and I hope many of them would be of use to you. Well, that's a slight promotion. Forgive me for that. Okay, let me start and straight away get into the topic. Now, we are going to talk about real life, which is probably the ground on which you play analysis. So you are all familiar with it. And also, it's a very interesting thing, and therefore some of the features of this real line should be clear to you if you want to feel comfortable doing analysis of that. That's why I have come up with this lecture. Let me open with a question. How does plants grow? This is one question. Almost the same thing is, how does the time flow? These are two crucial questions I am asking. Now, all of you would have observed that plants grow under conducive conditions. And how do you know that they grow? Because you can see every day the height of the plant is increasing, or a few more leaves are added to it, and so on. Second question is, how does time flow? I will come to the second one later. But if I ask this question, the answer I want in one of these two forms. Does it grow discretely or continuously? So the options are given, and I am sure that all of you would spring up and tell me that they grow continuously. This is your gut feeling about the whole thing. After all, had it been growing discretely, what would happen? You'll see that at some instances it will be jumping or jerking or something like that. This doesn't happen. Feel that it grows out of in a smooth flow of growth that you have. Same thing about the time. You feel that the time flows very smoothly, not discretely. It's not that you are jumping from one second to the other. Maybe your watch records only in seconds. Okay. But let us ask or try to ask the following question. What is it? How do you know that it is flowing continuously? Now, there is no way in which you can substantiate this, that it flows continuously. Why? Because there is a limitation for you to measure time. I believe if you can look into the net, the time can be measured precisely up to an error of 10 to the power minus 15 6 seconds. This is the current position. Maybe it has improved slightly because you know that every moment some new instruments or now some new system is invented to measure it more precisely. So this is absolutely essential in the case of investigating nature. Okay. That is the limitation. So you just do not know how you are not able to measure it, or you are not able to see at the moment the time span being more precise than 10 to the power minus 15 seconds. Therefore, for all such practical purposes, time grows discretely. Okay? But certainly that is not the case. Maybe a year later you will see some improvement on this particular number. See more and more precise. If you have to come back to this world after 100 years, you are going to see much more precision is available in these kind of measurements, and much more knowledge is added accordingly. So what you do is it's a hypothesis that time flows continuously. There is no experimental evidence to substantiate it, but it's your feeling. Now, the real line is essentially a manifestation of time flow. This is my point. Okay? That's why it is considered to be with no gaps. Okay? It's considered to be smooth. But let us see how mathematician conceives, or this was the question asked. How do you, because numbers were in use for a long time. And it was only in the 19th century and 20th century that some form of precise understanding of numbers were achieved. And so there was it was absolutely essential to do it more mathematically, because mathematicians have certain ways of doing things. First of all, there is certain logic which supports it, and it should be within that logical framework. And there's a culture about the whole thing, and this is visible in the construction of the real number system. So the theme of today's talk is how the real line is constructed. Okay, so we start with the system of natural numbers, or what you call just the numbers that you use for counting. Okay, so this is defined as the set of all numbers which is designated by 1, 2, 3. It's easily said, then explain what it is. Let us see how you get this. Now, it was Peano who gave a set of axioms which gives this system. So we start with Peano's axioms. There are 5 of them which describe the system. And you know, axioms are not something to be disputed, nor you attempt to prove any axiom. Because axiom is, see, when you say these are the set of axioms that define something, or you would have heard that group axioms are there, vector space axioms are there, then you know Peano's axioms defining what a natural number is. I mean, you say that if there is a system which agrees to these rules that you lay down, so rules of the game, then you call it the corresponding system. So here, any set which agrees to all these 5 axioms that you write down, this is what you call the set of natural numbers. So let us see what they are. So the first one is that 1 belongs to, which says 2 things. 1, n is non-empty, and there is at least 1 element in it, and it will be with a special status soon, and it is called 1, and 1 belongs to n. That is, there is something called the first element. So it will be clear. Now the second axiom is that for every x belonging to n, I designate an element of n by x. There exists a unique follower, unique natural number or element of n designated by x prime, called the follower of all these things are important. Once x is there, there is a unique follower or a unique successor, something that succeeds it. Okay, for instance, if you have 3, then it has a unique successor, and that successor we usually call 4. So there is exactly one element which succeeds the given element. What it says that every element of n, then it's a set. See, there is a kind of successor rule, namely that there is an immediate successor for every element. There is only one such element. That's why I put here unique. Okay. The third axiom is one is not the successor of any element. Which can be written as 1 is not equal to x prime for any x belonging to. That means 1 is not the successor, not a successor. Every other element is a successor. Also 2 is a successor of 1, 3 is a successor of 2, and so on. Okay, so 1 is not a successor of any element. The next thing is, see, we said that if you take one element, then it has a unique successor. Okay, right? Now what we are going to say is that you are going to talk about the predecessor. Because if x prime is the successor of m, then x is called the predecessor of x prime. So there is a relation. So I say that if x prime equal to y prime, then this implies, that means there is a unique predecessor. So the existence of a unique predecessor, existence of a unique successor. Now a predecessor is not available for 1. So except for 1, element 1. 1 does not have any predecessor at all. Okay. Now finally the induction axiom. This is very important. What it says is this: let script m be a subset of then if there are two conditions, one belongs to a script m, 2, the second condition is that x belongs to script m implies x prime belongs to . Just understand this condition. M is a subset of M. 1 belongs to M. X belongs to M implies X prime is also in M. Then M is the whole of. That means if M is script M is a subset of N with these two properties, then M is the whole of N. See, loosely talking, it says this: 1 is there, therefore its successor is there, therefore its successor is there, that is 3 is there, therefore its successor is there, and so on. So, all the successors are there. So you can get, you will see that M contains all these elements. Therefore M is equal to N. Now this is the whole idea of it. So these are the 5 axioms which describe what is called the natural system of natural numbers. Now within these 5 axioms, you can build a very nice system with a lot of structures imposed on n. Now this is what you are doing. I mean, see, all these are developed out of our day-to-day experience, as you can see. Now we'll go to addition. There are three structures on the system of numbers. One is addition, then there is this order, and three operations are, which gives you certain structures on the system. Now let us take up one by one. You look at addition. Let me define this. Okay. How do you define addition? How did you define addition in your school days? You defined it as, or your teacher would have told you that it is the repeated addition of 1. If you are to add 3 to 5, then add 5 times 1 to 3, 1 by 1. By which you mean 3 you take, add 1, you get 4, then you add another 1, you get 5, then you add 1 again, you get 6, likewise 7 and 8. Now this is how you do it. Okay, so we have to capture that idea in our definition. See how beautifully these things are done in mathematics. So the definition is that we define x plus 1. This is the first time we are using this symbol. This is defined as x prime for any x. Now the second condition is that x plus y prime equal to, is defined as x plus y prime. Now this is a bit soft. This is very easy to understand. Now let us see whether this gives you the addition. Check with an example. This is the best way to understand it. Okay. Also, you want to add 2 to 3. Let us work this out. You want to add 2 plus 3. What is 3? 3 is equal to, now this is a question that you are asking. So note, 3 is equal to 2 prime. Therefore 2 plus 3 equal to 2 plus 2 prime. Now you can apply this. If you apply this, this is going to be what? 2 plus 2 prime. What's the definition? Okay, but what is this? Again, you would note that 2 is 1 prime. Therefore, this is 2 plus 1 prime prime. But what is that? That's equal to 2 plus 1 prime prime. Am I right? Then the next one is, you have, what is 2 plus 1? 2 plus 1 is equal to 2 prime. Then you are taking the prime of that, you are taking the successor of that. So how do you get the number? You take 2, its successor is 3, each successor is 4, each successor is 5. So you get 2 plus 3. This is exactly what we learned in your schools. Okay? And this addition is described through repeated addition of 1. That's what you see here. So many primes come. Now, I'll just take out some of these things. keep these piano accents in your mind. You'll be using it left and right. In fact, see, the important thing in mathematics is when you do pure mathematics or rigorous mathematics, or axiomatic mathematics, you always play within the rules of the game, namely the axioms. You are never allowed to violate this. If you are violating it, then you are playing a different game. It's like chess. Chess, you know that it has certain structure, like 64 squares, alternately white and black, then two sets of 32 pieces to fight a war on the board. And then each entity has a specific movement. These are all the rules of the game. You are not supposed to violate them at any stage. Whether you are a novice or a grandmaster, use the same rules. But the game that you play may be quite different. Therefore, mathematics is exactly like that. So you have the axioms. You are not supposed to violate the axioms at any stage. Now, one of the things that you have to prove is that you have written down a definition, but before you call it a definition, you have to prove that such a thing makes sense on. So show such a thing makes sense on N. That needs some work because you have to play within these rules and show that this is consistent. Whatever you have written here is consistent, or in other words, given two elements, you can always add. So that's the thing that you have to prove. And having proved that, a lot of properties that you are used to follow from that, which can be proved. I mean, each one of them requires a proof. I am not going to do it. If I were to do it, I may have to take something like 40 or 50 lectures to complete the whole task. But let us look at that. What all things you get, you would have proved that x plus y plus z equal to x plus y plus z for every x, y, z belonging to n. That means it is associative. What does it mean? Let us read it. You take x, add to it the sum of y and z. That's the meaning of this bracket. This is equal to the sum of x with y added to z. It is immaterial which way you add it. Therefore, you can eventually discard this bracket. So this is what's called associativity. So you can prove all this. You have to prove within the axioms. Second one that you prove is that x plus y equal to y plus x. This is commutative. That means you take first x and then add y to it, or take first y and then add x to it, you get the same thing. So this is what commutativity, and you know that there are systems where commutativity is not valid. That's why you make a fun of it. So what we do is the following, and few things that we note is that y is not equal to y plus x. So when you add some natural number to y, you get a different number. Okay? You never get the same number. The fourth one. If y is not equal to z, then this implies all these are to be proved and has to play the game within these structures, and I'll tell you which book you can get into. And the fifth one is very interesting and very useful. You see that given x comma y belonging to n, either x equal to y or there exists u such that x equal to y plus u, or there exists v belonging to n such that y equal to x plus. Okay, let us see what it is. Let us work with an example, then it will be clear. So, given x and y, let us take 2 and 5. X I take as 2, y I take as 5. So, first of all, 2 is not equal to 5. That's clear. Then what are the other possibilities? Or there exists x is 2, y is 5. Of course, there does not exist any u such that x is equal to 5 plus u. Okay? But you see that 5 is equal to 2 plus 3. That means there exists a v such that y is equal to x plus v. Only one of the three will be true, not all the three or all two of them simultaneously. Okay, this is one of the properties of the number system. Incidentally, don't get confused. You might ask, okay, if you have x and y, x equal to 2, y equal to 5, why not write this as, why not take this as minus 3? We don't have minus 3 yet. Okay. In n, there is nothing called minus 3. Okay, we have only 3. Right? So you are confined yourself to the set n and to nothing else. We don't have the other parts of the number system readily available at the moment. So you forget that at the moment. Okay. This is a very, very important thing. What does it say? You are asking, you have a question here. The question is this: given x comma y belonging to n, you are asking, does there exist a solution of the equation you don't know u, you are given x and y. Okay, does there exist a solution? What you know right now is that in n, given x and y arbitrarily, sometimes there is a solution, not always. Okay, right? Right? For instance, if both x and y are the same, then there is no solution at all, because we don't have 0 yet. If you take x equal to 2, y equal to, or x equal to 2, y equal to 5, then there is a solution. If you take x equal to 5 and y equal to 2, then there is no solution at all because you don't have negatives here. Okay? So this is the crucial equation that is going to play. Don't just keep it in your mind. We'll come back to it quite like that. So what this criteria 5 says is that this equation has a solution in certain circumstances and not always. That's what we say. Okay, that gives us a new structure. So we introduce the next structure. So this is the addition. The next structure is what you call order structure. Order structure. What it says is that if you have x and y, then there may exist a u or may not exist a u. That means this equation may have a solution and may not have a solution. Okay. Suppose for given x comma y, this equation has a solution. Then we say x is less than, okay. For instance, 2 is less than 5, but 5 is not less than 2. Okay? So we write less than, we introduce the notion of less than, with this that gives an order structure. So given two elements, either x is less than y or y is less than x, but not both. So there is a well-defined order structure on the line. Okay? If on the other hand, suppose no solution, then we have y less than x or x greater than y. This is the same thing. This is the same thing. This is synonymous. Y less than x is the same as x greater than. Okay. Then of course, let me not, if I were to discover the properties etc., then I won't have much time. Now what you have on N, you have two structures, namely addition okay. Now we also introduce a new notation, namely less than or equal to. Less than or equal to means what? Given x and y, either x is less than y or x is equal to y. One of the two possibilities are there. You fuse them together and call it less than or equal to. Okay. For instance, 5 is equal to 5, 5 is less than 6. Okay. So only one of the things are valid. So x less than or equal to y if and only x less than y or x equal to y. This is also the use. And there is the analogous thing. If x is less than or equal to y, implies if and only if y is greater than or equal to x. So, x is less than y implies y is greater than x. Y greater than x implies x is less than y. Now, the important thing is that if they are not obvious, all of them have a needed. Okay. So you have so many properties associated with it. I do not want to list them because now you see it is important. There are two things. One, already there is an addition with respect to which certain properties are satisfied. Now you have an order structure. How these two interact together? This is a question that you have to mention. Now this is true for any mathematical system. If you have a mathematical system with the two operations, star and say two operations are there on the same set, then you have to say how these two, the elements here are, for instance, x star y will be defined, I will call this some operation y is defined. Now how these interact, these two operations interact together. For example, look at here. Suppose you have x less than or equal to y. Now what happens? X plus u is less than or equal to y plus u. Okay, addition is there, this is also there. So also x is less than or equal to y, x1 is less than or equal to y1, then you have x plus x1 less than or equal to y plus y1. All these things can be proved within the axioms and the definition of the order structure. Okay? And specifically a few things that are important here is x is greater than or equal to 1. 1. It is always greater than or equal to 1. Or 1 is the least element. Okay? And x is, y is less than y plus 1. Okay? Y is not equal to y plus 1. Y is less than y plus 1. Okay? So this property is right. Therefore, one of the things that you can say is that this is important. If A is a subset of N, then there exists A belonging to A such that A is less than or equal to X for every X belonging to. What does it say? It says that there is a least element in any subset of N. Okay? There is a smallest element in any subset of N. This is true. But can you say there is a largest element in every subset of N? It's not possible. For instance, you take just the even natural numbers. Does it have a greatest element? No. So this is the statement that we can make about N. Every subset in N has a least element. Okay. That is something about the order. Now come to the next one. The next structure is, so order has come out of this particular equation, namely X plus U equal to Y, whether it has a solution or not. This is the question. It is from there that the order structure has evolved. Now we introduce multiplication. How does multiplication come? Okay. What is multiplication? Multiplication is the repeated addition. No? What do I mean by that? You take 2 into 5 is essentially add 5 times 2. That means 2 plus 2 plus 2 plus 2 plus 2. That is 5 times you have added 2. This is how you have defined it. Now let us see whether we get it. So we give a definition. The first thing that you observe is that we postulate x into 1 is equal to x. And then we write x into y prime is defined as x plus, x y plus x. This is the definition. Okay. X prime is equal to x plus 1. This is one of the things that you can prove. Okay. Let us see whether this gives you the multiplication. Suppose you want to multiply 2 into 3. How do you write this? 2 into 3 is 2 into 2 prime. But what is 2 into 2 prime? This is equal to 2 into 2 plus 2. Okay? Yeah, I have used this. And let me again use this. So 2 into 2 is 2 into 1 prime plus 2. What is this? This is equal to 2 into 1 prime is, so this by definition, this is actually 2 into 1 plus 1 plus 2. But 2 into 1 is 2, so this is 2 plus 2 plus 2. Okay? But it is a repeated addition. 3 times you add 2 to itself. Okay? So that's what you get. So this is the school definition that you are familiar with, which has been put in this form. So this is true for every x, y belonging to. So you have now addition, order relation, and multiplication. Therefore, one has to talk about the interplay between them. Okay. So you have x into y into z equal to x into y z. This is what you call associativity. This is commutativity. X into 1 equal to x. That is of course a repetition of the first property. Okay. Right? So these 3 properties are there. Now you have to say how it interacts with addition. So you have the distributive property. This you can prove x into y plus x into z. Some work to prove it. It's nice to see how these things are proved. So you will learn plenty of mathematics by doing it. Okay. So the distributive property is there. Now this is also there. So you have x less than y. You take z, then you see that z into x is less than z into y. Okay? Right? And then all these properties you can list out. So I am not going into details of that. Then you have less than or equal to, that also has a similar properties. That is not important. I mean, those properties you can list out. Those four properties. What I mean to say is that now you see your number system is very rich. So the natural numbers is now endowed with addition, an order structure, and a multiplication. Three operations are there on it. Okay, three structures are on it, and there are properties pertaining to these three properties. So that constitutes what is called a set of natural numbers. One drawback, again you can ask the same question like, given x and y, what about the solution to this equation? Does it have a solution always? Suppose x is 2, y is 6, then you know that there is a solution. Okay? But suppose x is 2 and y is 5, there does not exist any u such that x into u is equal to, or 2 into u equal to 5. There is no solution in n. Okay, so it is not always true that this equation has a solution. So that is one of the drawbacks that you have. Okay, and you can show that x into y prime, oh, that's what we have in our definition. The definition has come from this. All these properties are there. Well, let me deal with that. Now you can keep talking or proving the properties of these things, but that's not important. My point is to give you the overall structure of the real life. Now the next step is going over to what are called fractions. Now you see, fraction is what? It is actually some integer by another integer, and the integer that you have below is not equal to 0. Therefore, you can conceive every p by q can be conceived as an ordered pair p q, this belonging to n cross there is no problem n cross n, because there is no 0 here. We have not introduced 0 at all. So this is it's an element of n cross n. Therefore, as it is, it's an element of n cross n. Okay? So you consider n cross n. Every element of n cross n is now considered as a fraction. Okay? Now what more you have? You can have again addition, order structure, and multiplication. This extended to fractions. Okay. So given a fraction p by q, p1 by q1 and p2 by p2, I don't want to write it in the order pair language. Use the conventional language that we have. This is, is p1 p2 plus p2 Q1 divided by Q1 Q2. Or in other words, the ordered pair whose first element is P1 Q2 plus P2 Q1, and the second element is Q1 Q2. Okay? So that is how you define it. Right? Okay? That's how the sum is defined there. Now one can prove these things. That is, you can prove all these properties mainly. See, here one thing is that we have not used anything new to define this. You know, it's a very sophisticated definition. Okay? It is not defined as P1 plus P2 divided by Q1 plus Q2, because that would have been your instinctive way of doing it. Okay, but it is not, right? So this is to facilitate a certain addition rule that is familiar to you from our day-to-day experience. So it is sophisticated. That is why addition of fractions is a problem for students, because it is not straightforward definition. It looks crazy because you are writing P1 Q2 plus P2 Q1. Why do all this acrobat? You might ask. Yes. Okay. But let us see the experience of this. Suppose you have a cake. Okay. And you have 1/3 of this plus half of this. What do you get? It's our experience. You take half of it and then 1/3 of it. What do you get? This is 1/3. What do you get? Okay. You can write this as, see, how do you write this? You divide everything more sharply, okay, into 6, because 6 is the what you call LCM of 2 and lowest common multiple of 2 and 3. Therefore, 1/2 will look like 3 by 6, and then what is this? This is 2 by 6, and there you write it as 5 by 6 because the denominator is the same. This is our addition. What is this? This 3? 3 is essentially, see, what you have is 6 is essentially your 2 into 3. And what is this 3? 3 is equal to 3 into 1 plus the other one is 2 into 1. That's what we have. Okay, that's how addition is defined. Because addition has to match with your experience. That's what we have to see. Now there are a lot of intricacies that come with this kind of thing. So let us explore this one. Okay. And then you can prove all the properties of addition, multiplication and so on. But one thing that you observe is this. You have suppose x1 by x2. Then you write this as y1 by y2. Of course, obviously when x1 equal to y1, x2 equal to y2, you write it that way. But even in other cases, you write it y. Already you have 1 by 3, 2 by 6, then 3 by 9, etc. They are all the same fraction from your experience. So you have to reflect that here. So you say that they are so provided the following holds, that is x1 y2 equal to x2 y2. right? They are the same. I don't write them equal. I am writing they are equivalent provided x1 y2 equal to x2 y1. x1 y2 equal to x2 y1. That's what you have. 1 by 3 is equivalent to 2 by 6. Why 1 into 6 is equal to 3 into 2. Okay. So this is the condition for equivalence. So this is so now what you have on n cross n, you identify every element with the fraction. You have an addition. You have a equivalence relation. Equal to notion is that. Then you have what you call addition, and then you have what you call an order structure. What do you mean by order structure? Now, given x1 by x2 and okay, we define an order structure. We say this is less than y1 by y2 if x2 y1 is less than x1. This is the definition. Similarly, we say x1 by x2 is equivalent to y1 by y2 if x2 y1 or you have x1 x2 is greater than sorry x1 y2 is less than x2. Made a mistake here. So x1 y2 is greater than. Now see, we are using our addition, multiplication and less than or greater than or equal to that we have defined on n to go to n cross n and define the structure. Because this is your notation that you are using, and this is if this is true. I mean, this is quite easy to find out because given x1 y2, x1 and y2, you have x1 y2. Given x2 and y1, you have x2 y1. Now given two natural numbers, you can compare them. So whether this is less than that or this is greater than that or they are equal. Accordingly, we introduce the order structure. Okay, that's what it is. Now one of the properties that you can prove is this, that given x2 and y1 by y2 either or x1 by x2 equivalent to y1 by y2 or x1 by x2 less than y1 by one of the three properties are valid. More or less, moreover, see, one of the important things that you can prove is this: x1 by x2 given, suppose it is less than y1 by y2, then there exists x1 by x2 is less than z1 by z2 less than y1 by. What does it mean? It means between two fractions you can always interpose a fraction, and whenever they are not equal. Okay, this is very, very, very important and deeper property of the fractions. Okay, now from fractions we manufacture the so-called rational numbers. Okay, so I just say what rational numbers are. Okay, then of course you have the multiplication defined, x1 by x2 into y1 by y2. That is pretty straightforward. This is x1 y1 by x2 y2. It is the ordered pair x1 y1 comma x2 y2. This is the definition of multiplication. So you have both addition, multiplication and order structure extended to the fractions. Okay, equality is now called equivalence because of the simple reason that things like 1 by 3 is not equal to 2 by 6. Because one is as points in n cross n, they are not the same, but they are having a relation, and that relation is what we call equivalence. Okay. Now from fractions we manufacture what are called rationals. This is what we do. Suppose you have got all the fractions which I denote by n cross n with all these structures plus, less than, and multiplication. Now you see that this is a very, very, very important thing that one does in mathematics. Take an element. Now we define a relation. Okay, we define a relation. We write x1 by y1 or x1 by x2 is related to y1 by y2 if and only if this is the definition. x1 y2 equal to x2 y1. This is the definition. So we say that x1 by x2 is related to y1 by y2 if x1 y2 is equal to x2 y1. What sort of relationship is this? So given two fractions, either they are related or they are not related. That's what we say. So given they are equivalent or not equivalent, which means either this may be less than that or the other one may be less than the other. Okay, as we have defined earlier. So what you do is choose an element, collect all the elements that are equivalent to it. Okay. Put them in a block. Okay. So given two elements in n cross n, either they are in the same block or they are in different blocks. Okay. Now you can prove that this is an equivalence What does it mean? It means x1 by x2 is related to itself. This is what you call reflexive. Then x1 by x2 is related to, this is reflexivity for every x1 and x2. Then you have x1 by x2 is related to y1 by y2 implies y1 by y2 is related to x1 by x2. This is what we call symmetry. Then you have x1 by x2 related to y1 by y2, comma, y1 by y2 is related to z1 by z2 implies x1 by x2 is related to z1 by z2. So this is what we call transitivity. It is not any type of relation, but it's an equivalence relation. That means it satisfies all the three properties, namely reflexivity, symmetry, and transitivity. Now you know that if on a set you have an equivalence relation, then you know that it partitions N into what are called equivalence classes. That means it is broken down into disjoint sets, and this can be written as a union of disjoint sets. And if you take one such subset, it will contain only elements which are equivalent to each other. If you take one element from one set and another element from another set, then they are not going to be related at all, okay, through this equivalence relation. So that's how this breakup comes. Okay, so you have collected all these sequences. For instance, example is, if 1 by 3 is here, then you have 2 by 6 is there, 3 by 9 is there, 27 by 81 is there, etc., etc. All these elements are there. They are equivalent to each other. Okay, but you won't see 1 by 2 in this, because 1 by 3 is not equivalent to 1 by 2. So that's what you have. So you have the equivalence relation, and that induces a partition. Now what one does is that this whole equivalent class of fractions is identified as a single ratio, and that is what you call a rational number. Okay, for instance, this whole block will be identified with 1 by 3, and there are no more common factors to it. Here there is a common factor, so you put them all together. Okay, so you can identify with something what you call 1 by 3, or you write this whole thing as 1 by the block containing 1 by 2. This may be 1 by 2. So on, or something like 17 by 19. If it is here, then the whole block will be denoted. Okay. Now the question that you ask is, so now you see we have a certain complexity here. What is that? It's a collection of all fractions. There is an equivalence relation that you have introduced. Now we have identified some of them together, and it is partitions into this. Can you define what is called, or can you extend the notion of addition, multiplication, and the order structure to this? The answer to this is yes, you can do that. Okay. So let me do that. is the same definition that you use. You say that 1 by or x1 by x2 plus y1 by y2, you define it as what? The class corresponding to this we have already defined. For example, I give an example 1 by 3, the block 1 by 3 plus the block 1 by 2 is equal to the block corresponding to 1 by 6. It's a definition. Okay? But there is a question. Is it well defined? Because the reason is this. After all, I may take 1 by 3 and 1 by 2 to construct, fabricate this 5 by 6. But somebody else might take this as 2 by 6 here and then take this for 3 by or what do you call 4 by 8. And then apply the rule of addition. What do you get? By definition, this will be 48 here, and then you have 16 plus, that's equal to 40 by. So the question is this the same as this block? That's the question. Is this block the same as this block? If you get it, well, then your addition is well defined. Otherwise, it becomes depends on the choice of the representative element. Okay, so we don't want that. So you see that, you easily see that the common factor here is what? You have what is that here? Yes. 8 is a common factor and you get 5 by, if you remove that, then you get 5 by 6. Okay. So this is equivalent to this, this is equivalent to this, implies this is equivalent to this. Okay. Therefore, you see that the addition is well defined. Similarly, you can work with the order structure. We say that x1 by x2, there is no ambiguity in this, y1 by y2, if and only if x1 by 2 is less than x2. Okay. Similarly, so any representative member you can use. Okay, that's the thing. You don't have to see, one person might pick up 2 by 6 to represent this. Another person might take up 27 by 81 to represent this. No matter who takes part, addition is well defined, the order structure is well defined, and also we say that x1 by x2 is equal to y1 by y2 if and only if x1 by x2 is equivalent to y1 by. That's the definition. Okay? That's the definition. Right? So this we have defined earlier. What is the meaning of that? x1 by 2 equal to x2 by 1. Right? So equality is defined, less than is defined, greater than is defined, addition is defined. Now multiplication also you can check this property. Into is well defined. This is defined as the class. This is the class. And you can also show that this is well defined. For instance, x1 by x2 is equivalent to x1 prime by x2 prime, y1 by y2 is equivalent to y1 by prime by y2 prime, then x1 y1 divided by x2 y2 is equivalent to x1 prime y1 prime divided by x2 prime y2. Let's see, that's what you have about the rational numbers. So these are the rational numbers that you have. So this whole system of blocks now constitute what is called the rational numbers. Now I can give another geometric interpretation of that, but let me not, well, maybe since I am permitted to go ahead with it, and let me go ahead with it. Then what you have is this. See, what is this n cross n? N consists of 1, 2, 3, let me mark this like this. 1, 2, 3, 4, and then this I have 2, 3, 4. So what are the points in n cross n? They are nothing but the lattice points. The lattice points are these junctions of these lines that you have. So you have this one, this is 1, 1, this is 2, 1, 1, 2, sorry, 2, 1, 1, 2, 1, 3, 1, 4, etc., etc. These are the points which turn out to be this. Now let me see how these fractions, each one is identified with a fraction. Okay? But which rational number it is identified? Okay? Yes. Okay. So this is, if you take this one, this one, this one, this one, what are these numbers? This is 1, 1, this is 2, 2, this is 3, 3, this is 4, 4, etc. They form a block. Okay. Now join this. See, this is 1, 2. Okay. 1, 2 with 2, 4. Okay. So you join this. So this line passes through this line. And so on. Similarly, if you take this, then this is going to go through these points. So each of these radial lines that pass through this ordered pair of points corresponds to a fraction, and that fraction has to do with the tangent of the line, or the tan of this line, or the cotangent of this line. You can okay, I will properly chosen. Okay, so they are the equivalence classes as you see here. Okay, this is a more Venn diagram type thing. This is a more concrete picture of this. So each one corresponds to a rational number. Okay, what are the main important change that has taken place? And this is what you have. If you start with natural numbers, now you see that there is a number next to a given natural number. Okay? Because every number other than 1 has both a successor and a predecessor. They are just lying next to it, in the sense that in between, you say that x and y are lying next to it. What does it mean? It means that in between x and y there is no other natural number. So the concept of nextness is there in. Do you have a similar concept here? Given a rational number, can you find a rational number next to it? What would this mean? This means that if there is a rational number here, say called P, and there is another rational number here, Q. Now, if Q lies next to P, there should be no rational number between P and Q. Okay, but that is not the case. Given two rational numbers, you always know that P plus Q by 2 lies between. You can prove this. There is a rational number in between, and this is by definition a rational number. Okay. Right? So there is no concept of nextness any more valid in what you call Q or the class of rational numbers. So no concept of nextness. So this is the biggest casualty. No nextness. That means, given Q, then you have the three, one of the three things happening, that is either P equal to Q, or P is less than Q, or Q is less than P. Okay? Right? So if P is less than Q, there exists another R belonging to Q such that P less than R less than Q. So there exists a rational number lying between P and Q. Once again this applies. So there are infinitely many rational numbers lying between two unequal rational numbers. Now this is one property that is markedly different from what you see on the natural numbers. So natural numbers have a discrete structure, but here you don't have that discrete structure. The concept of nextness is the casualty. It is completely gone now. But all the other properties do extend. You can extend addition, you can extend order relation, you can extend what is called the multiplication. But you don't have any more the concept of nextness. So we are working with the rational, I should say Q plus, because we are working with Q plus only right now. We are not going to Q minus or anything. Right. So let me go to the, let me just put this down and in the following format. So this is it. Then you have addition, multiplication. Three properties are there. Nextness is there. Is there? These are the usual properties. Now you have extended this. You have extended this to Q plus. You have extended this to Q plus. What do you have? You have extended addition. You have extended less than. You have extended. One more thing I want to say is that, every natural number can be discovered as an element of Q plus. How do you do that? So if you take a natural number n belonging to n, then n by 1, this class is in Q plus. And this can be identified n by 1. The block corresponding to n by 1 can be identified with n. Therefore, every natural number is embedded in what I call Q plus. So that is the structure that you have. Q plus addition is an extension of the addition here. Less than is an extension of the less than here. And multiplication is an extension of the multiplication here. This is clear because if you conceive m by n, m belonging to n, n belonging to n, then this is identified with m by 1 and this is identified with n by 1, and m by 1 plus n by 1 is identified with 1, and this is identified with m plus n. Okay, so addition is properly identified. So also you can show that is less than, greater than or equal to, all these can be identified. And so also multiplication, because m by 1 so m is identified with the block m by 1, n is identified with the block n by 1, mn is identified with the block mn by 1. So you see multiplication also is an extension of the concept of addition or of multiplication on n. Okay, but with one casualty, namely the nextness is lost. Once again, let us ask a few more questions. Like, suppose you have x1 by x2, y1 by y2, then you can actually show that there exists u1 by u2 such that x1 by x2 plus or more than 3, you can do this. Okay, right? If this is so, so given x1 by x2 the block, y1 by y2, three things are possible. Either the block is equal to, or greater than. One of the three things can count all the three. Okay, accordingly you can write down the conditions. So it is not that in all cases you can find u1 by only if this condition is satisfied, this is true. Okay, otherwise what happens is that if y1 by y2 is less than x1 by x2, and you have a v1 by v2 such that y1 by y2 block plus the block of v1 by v2 equal to the block of x1 by x2. Now let us look at this one. Suppose there is x1 by x2 and y1 by y2. So you ask the following question. Do you have a rational number p such that this is a question that you are asking. Does there exist? The answer to this is yes. Always there exists a p, which is of the sum u1 to okay. So what will be the u1 by u2 that you have? u1 by u2, u2 will have to be having the property that x1 by x2 is equivalent to y1 by y2. Or you should have u1 by u2, you can manufacture as y1 x2 by y2 x1. You choose this, then you have this property. So P will be equivalent to u1 by u2. Okay? Right? So this equation always has a solution. This equation has always a solution. So at least in the case of positive rational numbers, the equation P into psi equal to q has a unique solution. Whereas P plus psi equal to q has a solution only conditionally. Still we have not achieved got the question, got this question resolved. So our system is not big enough to solve this question for all P and Q. Okay? Whereas as regards to multiplication, yes, it is there. Okay? So this is the position you have. Now, one of the things that we normally do is try to put them on a line. Okay? Try to put them on a line. Okay? So you start marking 1 here, 2 here, 3 here, etc. N here, and plus 1 here. Now they form what is called the number system. Okay. Now what do you do? What is that you are doing? You are introducing things like m by n and all that p. So these are new entities that come in and start filling the place. So somewhere here I will put a barrier here, not marked yet. So you see that now you see all these points. Not all, but many of these points have a number. When they are all placed here, it goes even less than 1, goes greater than 1. But you see that a few things happen. You remember on n, we proved that every subset has a lowest element. In n, if you take any subset, It has a minimum in that set. In Q, if you take, there is no minimum element. For instance, in N, if you take the whole of N, what is the lowest element? The smallest element that you have is 1, according to the order structure. But suppose you take Q plus, what is the smallest element? There does not exist a smallest element in Q plus. Why? Because suppose there is a smallest element, then this is of the form x1 by x2. Now, if you look at this one, x1 by 2x2. x1 by 2x2 is always less than x1 by x2. So, if this were the smallest element, then you have something still less than that in that set. Okay? So, there does not exist a smallest element in Q plus, whereas in N there exists a smallest element, namely 1. That's one special feature that you have. So, we have the following properties now. Every natural number has a unique natural number next to it to its right. Every natural number other than 1 has a natural number to its right and to its left. What you call the successor and the predecessor. Now there is a concept of nextness in N. This is essentially a discrete structure. So N has a discrete structure. Given any non-empty subset of N, there exists a unique smallest number. N has no largest number because if N is there, N plus 1 is there. Further, the equations A plus X equal to B has a solution sometimes and not for all choice of A and B, this equation has a solution. Similarly, the equation Ax equal to B does not necessarily have a solution. Sometimes it has to be. For instance, if you take A equal to 3 and B equal to 6, then there exists a natural number 2 such that 3 into 2 equal to 6. So sometimes it has a solution, but it doesn't have. But when you come to rationals, you see that every natural number is a rational number. So that is what I said, N is embedded in Q plus. Okay? Then the concept of nextness wither away. You don't have any more the concept of nextness. Now this is really frightening in some way, because a word we are used to is something where you have the concept of nextness. You are familiar with. Okay? What is to your day-to-day experience, the nextness is there. You don't feel the absence of that. Okay? But now you are running into a world of fantasy through fractions, or what you call the rational numbers. So the rational numbers Q plus that you have defined does not have the concept of nextness. This is something which you cannot immediately conceive with your day-to-day or reconcile with your day-to-day experience. Now this is something very interesting. Now you have also the equation P plus X equal to Q, given P and Q, need not have a solution. So that problem has not been solved at all. But when it comes to the following equation, namely Px equal to Q, this problem has been solved. It is given P and Q in Q plus, there exists a rational number x such that, or u such that Pu is equal to Q. So this equation always has a solution. So that's a bit of a solace. So we have extended this and got one irritant out of our way. Okay. It says that our extension is still not completely satisfactory, but it is satisfactory to some extent. That is, partially it has achieved the existence of the solution of the A equation, not fully the linear equation that we have. The linear equation will be something like Ax plus b equal to c. Even A, B, C, does it have a solution? Okay. You cannot say this. But if your equation is something like Ax equal to b, where A and B are both positive rationals, then it has always a solution. So partially it has been met. Okay. So this is the position that you have. Now I think I stop this talk at the moment here, and certainly I will continue with it to take it to the next level soon. That is, extend the rationals to the reals, and that has been our objective. I have not completed it, but this will be available in my YouTube channel in a day or two. So those who have seen this can always log on to that part and enjoy it. So thank you very much. At this stage, I will return with the real life. Thank you. Hello.
Sir.
Thank you very much.
Thank you, sir.
This was really wonderful. Now I will put the remaining portion of this, namely the real line structure, maybe in another day.
Okay, sir.
Okay, I probably need some rest or something like that, and then we will take it up.
Okay, sir.
Okay. So I will continue from here and then put the whole real line completed next class.
Okay,
So
sir.
tomorrow maybe I will do it, or maybe this afternoon I will do it, or sometime in the night or sometime.
Okay.
Anyway, I will talk to Biju and then we will work it out together. And after that, it will be available for you on my, what is called the classroom.
YouTube, Krishna's classroom.
Yes.
Okay.
Thank you very much. It was really wonderful. It's my first experience. I should say it's my first experience. So I don't know whether I was really a bit nervous about the whole thing, because I don't know how the technology will work. The interface is very important. Now you are all used to doing this. I am not used to, but it looks really a wonderful experience, I must say, and the possibility is enormous. Okay, thank you very much once again.
Thank you, sir.
Yeah,
സാറേ വളരെ നല്ല ലെക്ചർ ആയിരുന്നു സാർ.
thank you.
നമുക്ക് ഡിസ്കഷൻ എന്തെങ്കിലും ചോദിക്കാനുണ്ടോ? ചോദിക്കാൻ തോന്നുന്നു അല്ലേ?
അതെ ചോദിക്കാം, തീർച്ചയായിട്ടും. യെസ്
സാറേ, വളരെ നല്ല ക്ലാസ് ആയിരുന്നു.
താങ്ക് യു.
മാത്രമല്ല ഇത് റെക്കോർഡഡ് വേർഷനിൽ വരുന്നത് കൊണ്ട്
അതെ
പിന്നീടും കാണാം. അത്
ഞാനിതൊന്ന് എലാബറേറ്റ് ആയിട്ട് ചെയ്യണം എന്ന് വിചാരിച്ചാട്ടോ.
ഓക്കെ സാർ. ടൈം ഈസ് ദ കൺസ്ട്രെയിന്റ്.
അത് മാത്രമല്ല, ഇതിന്റെ ഒരു കംപ്ലീറ്റ് സ്കീം ഒരു നല്ലൊരു ജർമ്മൻ ബുക്ക് ഉണ്ട്. അതിന്റെ ഇംഗ്ലീഷ് ട്രാൻസ്ലേഷൻ ഇസ് ഓൾസോ അവൈലബിൾ.
ഓക്കെ സാർ.
ഇറ്റ്സ് കോൾഡ് ഫൗണ്ടേഷൻസ് ഓഫ് മാത്തമാറ്റിക്കൽ അനാലിസിസ് by Landau.
Okay.
Maybe I will write it out next time on my lecture. The remaining part I will write where it is available and so on, so that if those who are interested can download that book from the net. അപ്പോൾ അത് ഉപയോഗിക്കാൻ പറ്റും. കാരണം ഈ നമ്പർ സിസ്റ്റത്തിന്റെ കൺസ്ട്രക്ഷൻ വളരെ വളരെ ഫാസിനേറ്റിംഗ് ആണ്. അത് കൃത്യമായിട്ട് അറിഞ്ഞാൽ മാത്രമേ അനാലിസിസിലെ എപ്സിലൺ ഡെൽറ്റ ഓപ്പറേഷൻസ് മനസ്സിലാവുള്ളൂ.
Okay, sir.
So I will go to that next time.
Yes.
After getting the real line, I'll make some remarks about it.
Okay.
So I will see, which will give you a complete understanding of why you talk about something like xn converges to 0. What do you say? You say that given epsilon positive, there exists a n such that mod xn is less than epsilon for all n greater than some particular n. This is the definition that you do. And
Okay.
why that gives you xn goes to 0 is a question. Okay. So
Okay.
that will be clear only when I just give you the yeah, it will be available there. And also you can communicate with me on the dedicated email ID.
Ganitha Vicharam.
The email ID is also there exclusively for that channel.
Okay. Ganitha Vicharam.
So, right. So if you write to me, I can give you, you know, explanation, etc., on that email ID.
നല്ല ക്ലാസ് ആയിരുന്നു.
Thanks.
ഇന്നത്തെ വലിയ ഡൗട്ട് അങ്ങനെ ഉണ്ടായിട്ടില്ല. സാറിന്റെ ഇനി വരുന്ന ക്ലാസ്സുകൾ കേൾക്കാം. പിന്നെ ഇന്നടുത്ത് നമുക്ക് എല്ലാവർക്കും നമ്മൾ ആദ്യം ചെറിയ ആയിട്ട് നമ്മൾ പഠിക്കുന്നത് നമ്പർ സിസ്റ്റം നമ്മൾ ജസ്റ്റ് 1+1 = 2 നമ്മൾ അങ്ങ് പഠിച്ചു കഴിഞ്ഞു. അപ്പോ എന്നേരൊന്നും നമ്മൾ ആരും ഇത് അറിയുന്നില്ലല്ലോ. അപ്പോ ഇപ്പൊ സാർ ഈ ക്ലാസ് ഒക്കെ എടുത്തു കഴിയുമ്പോൾ നമുക്ക് തോന്നും ഏത് തിയറി ആണോ ഫസ്റ്റ് ഉണ്ടായത് അല്ലെങ്കിൽ ഇതാണോ എന്നുള്ള ഒരു കൺഫ്യൂഷൻ ആകും.
ഇത് ഈ ക്വസ്റ്റ്യൻ ഇത് ലാൻഡോന്റെ ഒരു ബുക്ക് ഉണ്ട്. അതിൽ ഞാൻ നേരത്തെ ഒരു ബുക്കിനെ പറ്റി പറഞ്ഞു. ആ ബുക്കില് ലാൻഡോ പറയുന്നുണ്ട്, ലാൻഡോ ഇത് എങ്ങനെയാ കൺസീവ് ചെയ്യണമെന്ന് വെച്ചാല് ലാൻഡോവിന്റെ മകള് പോയിട്ട് ലാൻഡോവിനോട് ചോദിക്കുന്ന ചോദ്യം. ലാൻഡോ എന്നുള്ള ഒരു വലിയ നമ്പർ തിയറിസ്റ്റാണ്. ഒരു കാലത്തെ ഗോട്ടിങ്ങൻ യൂണിവേഴ്സിറ്റിയിൽ ഉണ്ടായിരുന്നു. അപ്പൊ അദ്ദേഹത്തിനോട് ചെന്ന് അദ്ദേഹത്തിന്റെ മകളെ, ഐ തിങ്ക് ഷീ വാസ് ഡൂയിങ് സം കെമിസ്ട്രി ഓർ സംതിങ്, വൈ 1+1 = 2 എന്നുള്ളൊരു ചോദ്യം ചോദിക്കുന്നുണ്ട്. അപ്പോഴാണ് ലാൻഡോ ആലോചിക്കുന്നത് there is enough room to write a book on that. അങ്ങനെയാണ് ഈ കംപ്ലീറ്റ് സിസ്റ്റം ഇവോൾവ് ചെയ്യുന്നത്. ഇറ്റ്സ് എ ബ്യൂട്ടിഫുൾ ബുക്ക്. How starting from Peano's axioms you systematically build these natural numbers to what is called rationals or positive rationals, and then to positive real numbers, then to the whole real number system. That's how he proceeds. Okay, so which at each stage some new extra structure is added. So you get the whole real line evolving starting from natural numbers in a very systematic way. And that gives everything, or tells you everything about how to work in analysis. All the techniques that you use in analysis are there when you start proving each one of these statements. And that's very interesting. It's a nice book. I'll write down the title of the book, etc. next time in the remaining lectures.
Okay, sir. Thank you.
എനിക്ക് 1-2 കാര്യങ്ങൾ സൂചിപ്പിക്കാനുണ്ട്. കാരണം സാറിന്റെ യൂട്യൂബ് ചാനൽ ഇന്നാണ് റിലീസ് ചെയ്തത്, പബ്ലിക്കിന് അവൈലബിൾ ആയത്. അപ്പൊ ഓൾറെഡി 84-85 സബ്സ്ക്രൈബേഴ്സ് ആയിട്ടുണ്ട് സാറിന് ഇന്ന് തന്നെ ഓൾറെഡി. ഓക്കെ. അപ്പോ അതില് ഞാൻ പറയുന്ന കാര്യം, ഇപ്പോഴ് സാർ ഇപ്പൊ തുടങ്ങി വെച്ചിരിക്കുന്ന വർക്ക് ഇന്റഗ്രേഷൻ ആണ്, റീമാൻ ഇന്റഗ്രേഷൻ ആണ് ഇപ്പൊ എടുത്തു വരുന്നത്. അപ്പൊ റീമാൻ ഇന്റഗ്രേഷനിൽ സാർ ചെയ്തിരിക്കുന്ന ഭാഗത്തിൽ ആദ്യത്തെ 3-4 ലെക്ചേഴ്സ് എനിക്കത് ആദ്യം തന്നെ കാണാനുള്ള ഒരു ഭാഗ്യം ഉണ്ടായിട്ടുണ്ട്. അപ്പൊ ആ ലെക്ചേഴ്സിൽ സാറ് ശരിക്കും എന്തിനാണ് ഇന്റഗ്രേഷൻ പഠിക്കുന്നത് എന്നുള്ള ഒരു ലൈനിൽ തന്നെയാണ് തുടങ്ങുന്നത്. നമ്മൾ ഹൈസ്കൂൾ ക്ലാസ്സിൽ പഠിച്ച ഒരു ഐഡിയയിൽ നിന്നും തുടങ്ങി മുന്നോട്ടേക്ക് വരികയാണ് ചെയ്തത്. അപ്പൊ എനിക്ക് തോന്നുന്നു ആ ലെക്ചേഴ്സ് ഈവൻ +2 സ്റ്റുഡൻസിന് പോലും അത്യാവശ്യമുള്ളതാണ്. പലപ്പോഴും വിദ്യാർത്ഥികൾ പലരും ചോദിക്കുന്നത് എന്തിനാണ് നമ്മൾ ഇന്റഗ്രേഷൻ പഠിക്കുന്നത്, വെറുതെ കുറെ സൂത്രവാക്യം ഇങ്ങനെ ഫോർമുലാസ് ഇങ്ങനെ പഠിച്ചു പോന്നു, എന്താണ് ഇത് എന്നുള്ളതിന്റെ ഒരു നല്ലൊരു ഇതാണ് വ്യൂ. അപ്പൊ എല്ലാവരും കാണണം എന്നുള്ള ഒരു റിക്വസ്റ്റ് ഞാൻ കൊടുക്കുകയാണ് വിദ്യാർത്ഥികളോട് പ്രത്യേകിച്ച്. കാരണം നമ്മൾ ഈ പഠിക്കുന്നതൊക്കെ പ്രത്യേകിച്ച് MSc-ക്കൊക്കെ നമ്മളിങ്ങനെ നിരന്തരം കണ്ടുകൊണ്ടിരിക്കുന്ന കോൺസെപ്റ്റ്സ് ആണ്. അപ്പോ കൃഷ്ണകുമാർ സാറിനെ പോലെയുള്ള ഒരു എമിനന്റ് ടീച്ചർ എടുക്കുന്ന നമുക്കിത് നേരിട്ട് പഠിക്കാൻ പറ്റുന്ന ഒരു സാഹചര്യം ഇപ്പോൾ കൈവന്നിരിക്കുക. ഞങ്ങളൊക്കെ ശരിക്കും പറഞ്ഞാൽ ഞങ്ങളുടെ കോളേജിലൊക്കെ സാറിന്റെ സാന്നിധ്യം കുറെ വർഷങ്ങൾക്ക് മുമ്പ് സാർ സ്ഥിരമായി വരുമായിരുന്നു. പിന്നീട് സാറിന് ഈ യാത്ര ഇത്രയും ദൂരം യാത്ര ചെയ്യണമല്ലോ എന്ന് വിചാരിച്ചു ഞങ്ങള് സാറിനെ ബുദ്ധിമുട്ടിക്കാറില്ല. പക്ഷെ ഇത് വലിയൊരു ചാൻസ് നമുക്ക് കൈവന്നിരിക്കുകയാണ്. ഓൺലൈൻ മീഡിയം വഴി സാറിനെ നമുക്ക് തൊട്ടടുത്ത് കിട്ടിയിരിക്കുകയാണ്. അപ്പോ SN കോളേജിനാണ് ഒരു ഭാഗ്യം കിട്ടിയത്. കാരണം സാറിന്റെ ആദ്യത്തെ വെബിനാർ നിങ്ങളുടെ കോളേജിനാണ് കോർഡിനേറ്റ് ചെയ്യാൻ പറ്റിയത്.
So viewers are too lucky.
Thank you. അല്ല ഞാൻ
യൂട്യൂബ് ചാനൽ സ്റ്റാർട്ട് ചെയ്യുന്നത് തന്നെ നമ്മളെ വെബിനാറോട് കൂടിയാണ് എന്നുള്ളത് നമ്മള് ഭയങ്കര അഭിമാനത്തോടു കൂടി.
അതെ. അല്ല ഞാന് ഈ ഒരു ചാനൽ തുടങ്ങാനുണ്ടായ ഒരു കാരണം, ബിജു എന്നോട് ചോദിച്ചു എപ്പോഴെങ്കിലും ഒരു വെബിനാറിൽ പങ്കെടുക്കാൻ പറ്റുമോ എന്നുള്ളതാണ്. അപ്പൊ എൻ്റെ അടുത്ത് യാതൊരു സാധനവും ഇല്ല, ഒരു മൊബൈൽ ഒഴികെ വേറെ ഒന്നുമില്ല. മൊബൈൽ ഉപയോഗിച്ചിട്ട് ഇത് ചെയ്യാനും പറ്റില്ല. പിന്നെ ഞാൻ അത്ര ഒരു എക്സ്പെർട്ട് ഒന്നല്ല ഈ എന്താ പറയുക നമ്മുടെ ലാറ്റക് ഉപയോഗിച്ചിട്ട് ഇത് അതിന് വേണ്ട സപ്പോർട്ടിങ് സാധനങ്ങളൊക്കെ ഉണ്ടാക്കാനും അല്ലെങ്കിൽ ഒരു സ്ലൈഡ് ഉണ്ടാക്കാനും. ഒന്നാമത് എനിക്ക് അതിനോട് വലിയൊരു ഇഷ്ടമില്ല. എനിക്ക് ഇഷ്ടം ഇങ്ങനെ ബോർഡിൽ വർക്ക് ചെയ്യാനാണ്. അപ്പൊ ഞാൻ ഇങ്ങനെ ആലോചിച്ചു ഇത് എങ്ങനെ ഒരു ബോർഡ് കൂടിയിട്ട് ഒരു ക്ലാസ് റൂം എങ്ങനെ ഉണ്ടാക്കാം എന്നുള്ളതിനെ പറ്റി ആലോചിച്ചപ്പോഴാണ് ഇങ്ങനെ ചില സാധനങ്ങളൊക്കെ. ഐ തിങ്ക് ബിജു വാസ് ഗിവിംഗ് മീ സച്ച് എ magnificent support for the whole thing. There were some others also who gave me a lot of support. And somehow within 1 month, I think I could assemble all the necessary gadgets to start this classroom. I have already recorded something like 7 lectures on integration and put it on the classroom. Today only it was released. Until that time it was on private circulation. Like Biju is still helping me to edit some of these lectures. He is doing a magnificent work. So I think soon, in another 3-4 days time, I think all the 7 lectures will be available. And there may be, whenever I get time, I may put the next one. So it's still not complete. A number of lectures are scheduled to be done on this channel. And my ambition is this. I want to, I know from my experience where the difficulty lies for students in understanding several concepts. For instance, this idea of working on integration came because I know that Lebesgue integration is a difficult concept for people, especially understanding the concept of measure. Measure is something which is, not digested properly by people. So I thought that maybe I could, say something about measures because I have a way of introducing measure, and which if I want to give that, I have to do first Riemann integration. So I just explored through some lectures on Riemann integration, and they are already coming up. And once I complete that, I will just list out the drawbacks of Riemann integration or what are the inadequacies. I won't say drawbacks, the inadequacies to cover sufficiently large class of functions, and then go to introduce the concept of Lebesgue integration. Now this is my plan. So every sort of lecture series that I will give on this will be of interest to graduate students if they are learning mathematics. Already another series is evolving with this the Devagiri College. Their IQAC has recorded some of my lectures. 7 of them are already there on linear algebra, and I have started off with a very definite plan, but because of the corona, I think the recording stopped. And now I think we will resume it soon. If they are not resuming it, they are not in a position to resume it, I will do it on my channel, certainly the remaining part of it. What I have in mind is this. This is specifically to the answer to these questions. Why or can you diagonalize every linear transformation? This is one of the questions I have. Is it possible to diagonalize it? The second question I have is, if that is not possible, in the other cases, what can you do? Can you get very elegant, simple representations for that? In the case of diagonalization is possible, you can get a diagonal representation. But in other cases, what can you do? So there you get a, come to what is called rational canonical form, or what you call, say, this, some other elementary forms that you come across, which is slightly more complicated than the diagonal ones. So that series I will complete. If they are not doing it, I will do it on my channel. So it will be available. And then I have plans to, do quite a lot on, say, things like other areas, like many specific questions on analysis or complex analysis, or differential equations, or partial differential equations. All these various topics I intend, putting up my lectures on this channel. So it's a vast thing. I mean, as long as I can do it, I will do it. I'll keep doing it. Anyway, it's a nice pastime for me also. Thank you very much.
ഞാൻ സാറിന്റെ ക്ലാസ് മുഴുവൻ കേട്ടു സാർ.
ശരി, നീ എന്റെ ബാക്കിയുണ്ട്. ബാക്കി ഞാൻ നാളെ മിക്കവാറും ചെയ്യും.
ഇതേമാതിരി യൂട്യൂബ് ചാനൽ അല്ലേ?
അല്ല, ഇതിന്റെ കണ്ടിന്യൂവേഷൻ ആയിട്ട് ചെയ്യും.
ചെയ്യൂല്ലേ? ഓക്കെ.
ഇത് ബി അവൈലബിൾ. അത് കഴിഞ്ഞിട്ട് അത് എഡിറ്റ് ചെയ്ത് 2-3 ഭാഗമായിട്ട് ഇട്ടാല് കുട്ടികൾക്ക് യൂസ്ഫുൾ ആവും. സോ ഐ വിൽ കംപ്ലീറ്റ് ഇറ്റ്. ഐ വിൽ ഗെറ്റ് ദ സ്ട്രക്ചർ ഓഫ് ദ റിയൽ ലൈൻ കംപ്ലീറ്റ്ലി. അതാണ് പരിപാടി. എന്തായാലും ഒരു നല്ല എക്സ്പീരിയൻസ് ആയിരുന്നു. ഐ എം വെരി ഹാപ്പി ദാറ്റ് സച്ച് പ്രോഗ്രാംസ് ആർ ഓൺ.
ഇങ്ങനെ എടുക്കുന്നത് ശരിയായി അല്ലേ? ഇപ്പൊ ബോർഡ് ഇങ്ങനെ വെച്ച്, അല്ല ബോർഡിൽ ഇങ്ങനെ എടുക്കാൻ ഇപ്പൊ സാറിന് ബുദ്ധിമുട്ടൊന്നുമില്ല. നല്ല ക്ലിയർ ആണ് ഇപ്പൊ ബോർഡും.
അതെ, ബോർഡ് ക്ലിയർ ആണ്. ബോർഡ് ക്ലിയർ ആണ്. ഇത് സാധാരണ നാച്ചുറൽ ക്ലാസ് റൂം പോലെ തന്നെ ഉണ്ട്. അറ്റ്ലീസ്റ്റ് ഓൺ മൈ കമ്പ്യൂട്ടർ ഇറ്റ് ഈസ് കമ്മിങ് അപ്പ് ദാറ്റ് വേ. ഐ ഡോണ്ട് നോ ഹൗ പീപ്പിൾ സോ ദാറ്റ്. അവിടെ കുട്ടികൾ കണ്ടപ്പോ എന്തായിരുന്നു അവരുടെ എക്സ്പീരിയൻസ് എനിക്ക് അറിയില്ല. നന്നായിരുന്നു,
വളരെ നന്നായിരുന്നു സാറേ.
അതെയാ, ക്ലാരിറ്റി ഉണ്ടായിരുന്നോ?
മൊബൈലിൽ കാണുമ്പോൾ കുറച്ച് ചെറുതായിരിക്കും, ബട്ട് ഞാൻ കമ്പ്യൂട്ടറിലാണ് കണ്ടത്. അപ്പോൾ കമ്പ്യൂട്ടറിലൊക്കെ കാണുമ്പോൾ ചെയ്യാൻ യഥാർത്ഥ ക്ലാസിന്റെ എഫക്ട് കിട്ടുന്നത്, വലിപ്പത്തിൽ വലിയ സ്ക്രീനിൽ ചെയ്യുന്നത്. പിന്നെ നിബിഡിച്ച ഒരു കാര്യം കൂടി പറയാം, ഈ ഗ്രൂപ്പിലുള്ള സ്റ്റുഡൻസിന്റെ ശ്രദ്ധയ്ക്കാണ്. അടുത്ത ദിവസം തന്നെ ഇരിട്ടി മഹാത്മാഗാന്ധി കോളേജ് സാറിന്റെ ക്ലാസ് റൂം എന്നുള്ള ക്ലാസ് റൂമിനെ ഒന്ന് കോർഡിനേറ്റ് ചെയ്യാൻ വേണ്ടിയിട്ട്, അതായത് വിദ്യാർത്ഥികൾക്ക് ഡിസ്കഷൻസ് ഒക്കെ പ്രോത്സാഹിപ്പിക്കാൻ വേണ്ടിയിട്ട് ഒരു ഗൂഗിൾ ക്ലാസ് റൂം അടുത്ത് തന്നെ ആരംഭിക്കുന്നുണ്ട്. അതിന്റെ വിവരങ്ങൾ ഗ്രൂപ്പിൽ ഷെയർ ചെയ്യുന്നതാണ്. അപ്പോ സാറുമായിട്ട് ഡിസ്കസ് ചെയ്യാനും തുടർന്ന് ഗൂഗിൾ മീറ്റുകളും ഒക്കെ ക്ലാസ്സുകളൊക്കെ ഒരു വളരെ സിസ്റ്റമാറ്റിക് ആയിട്ട് ചെയ്യാൻ വേണ്ടിയിട്ടാണ് ഞങ്ങൾ ആ ഗ്രൂപ്പ് ഫോം ചെയ്യുന്നത്. അപ്പൊ താല്പര്യമുള്ള വിദ്യാർത്ഥികൾ ആ ഗ്രൂപ്പിൽ ചേരണമെന്ന് ഞാൻ റിക്വസ്റ്റ് ചെയ്യാണ്. കാരണം നമുക്ക് ഒരുമിച്ച് കുറെ കാര്യങ്ങൾ സാറിന്റെ കയ്യിൽ നിന്നും നേടിയെടുക്കാൻ സാധിക്കുന്നതാണ്. ഞാൻ ആദ്യം ഇൻട്രൊഡക്ഷനിൽ പറഞ്ഞതുപോലെ തന്നെ സാറ് വളരെ വിദ്യാർത്ഥിയായിരിക്കുമ്പോൾ തന്നെ വളരെ മികച്ച പ്രകടനം കാഴ്ചവെച്ച വ്യക്തിയാണ്. അപ്പോൾ ടീച്ചർ എന്നുള്ള നിലക്കും നാഷണൽ അവാർഡൊക്കെ വാങ്ങിച്ച വ്യക്തിയാണ്. അപ്പൊ നമുക്ക് സാറിന്റെ കയ്യിൽ കുറെ കാര്യങ്ങൾ ക്യാച്ച് ചെയ്യാനുണ്ട്. അപ്പൊ വിദ്യാർത്ഥികളോട് എന്റെ ഒരു റിക്വസ്റ്റ്, നിങ്ങൾ സജീവമായിട്ട് ആ ഗ്രൂപ്പിലൊക്കെ പങ്കെടുക്കണം എന്നുള്ളതാണ് പറയാനുള്ളത്.
ഓക്കെ സർ, ഒഫീഷ്യലി ഇതിന്റെ അവസാന ഭാഗത്തേക്ക് പോവാന്ന് തോന്നുന്നു.
A warm and graceful day to our most valued honorable chief guest and lecturer Professor V. Krishnakumar sir, respected Dr. Bijimon sir, respected teachers and dear students. As we all know, real analysis is a branch of mathematical analysis which deals with the behavior of real numbers, sequences and series of real numbers and real functions. Real analysis enables the necessary background of measure theory, and it has a great impact in our upcoming world. It's my privilege to propose a vote of thanks and acknowledge the contribution of those who work in our happen. Of mathematics department,
Dr. V. Krishna Kumar sir, who spared his time from his busy schedule to share his thoughts and ideas. He has been an inspirational figure for all of us. Sir, your presence itself has made the program a successful. Today, I had an opportunity to hear from you, sir, and I hope your knowledge has proved to be a great enlightenment to each of us. First, when we heard about a class on real analysis, we thought it would be a discussion on properties and so on. But sir, this is indeed a different one. Even a beginner grasp it quickly. So proud to know that, sir, your YouTube channel has been inaugurated for our webinar. Thank you, sir, for your informative class. Next, I would like to thank Dr. Bijumon sir, Associate Professor and Head of PG Department, MG College, Iriti, who have immensely supported and helped us to do our best. Without your technical support, we couldn't have done this, sir. Krishna Kumar sir for this lecture. Thank you, sir. Next, I would like to thank our HOD, Mrs. Divya PM, for her untiring efforts to make this webinar happen. Thank you, ma'am. In addition to that, I would like to thank Mathematics Department of SN College for arranging this webinar for us. Our sincere gratitude goes to all teachers who have assembled here. Thank you, teachers. I also take this opportunity to thank our student coordinator, Naveen Krishna, who has put a great effort behind this program. Thank you, Naveen. Next, I would like to thank all the students for their enormous cooperation. Last but not least, on behalf of Mathematics Department, thank you to one of you.